Mullard Space Science Laboratory at UCL, and I work there with Tom Kitching. And it's based on these kind of 3 papers that you see at the bottom there, but I will point out what is relevant to what if you're interested in following it up. So let me start with a bit of context. Why are we looking at this now? So we're kind of standing on the precipice of the next generation of weak lensing cosmic shear surveys. We've got, most soon Euclid coming up, which a lot of people here are involved in, I think. But we also have the Rubin Observatory and then the Nancy Roman Telescope, which will also come up soon. But the thing about these upcoming cosmic shear surveys is that they will offer more than an order of magnitude leap in the precision of our data. So what that means is that we really need to now ensure that the accuracy of our theory can keep up with the precision of our data. And I'm kind of primarily focused on Euclid, but essentially the things I look at are also very much applicable to the other 2. So I know not everyone here is necessarily familiar with what weak lensing is and how it works. So I'll just kind of do a quick overview. So what we say when we refer to what we're talking about when we refer to weak lensing is basically the fact that the images that we see of distant galaxies are actually gravitationally lensed because of all the large-scale structure of the universe between us and those galaxies. So you can just think of you can see there a faraway galaxy. The light that's coming from it is going to be distorted a tiny bit by basically everything it encounters in its path, and the final image will be distorted. And this can be a really powerful probe of dark energy because it's also sensitive to the geometry of the universe. This effect has 2 components. One is known as the convergence, and the other is known as the shear. So the convergence is basically magnification. It's basically an isotropic increase or decrease in the size of the object, whereas shear is kind of anisotropic stretching of the object that makes circular distributions of light more elliptical. And the thing about these is that they both depend on the total matter density along the line of sight and the geometry of the universe. So the quantity they actually depend on is basically the density contrast at a given kind of redshift and position on the sky. But the values of these effects for individual galaxies are very low. So to get a high enough signal to noise ratio where we can actually use them for cosmology, we basically need to use statistical measures. But it's not as simple as just taking the ensemble average of the convergence of the shear, because that would just be 0, because since it's directly related to the density contrast, the average of the density contrast, of course, is just 0. So the first non-trivial statistical measure is the 2-point statistic. So basically the correlation at certain distances of 2 objects. And in particular on this talk, I'll be focusing on the Fourier conjugate of the correlation. So that's the angular power spectrum. So how do we actually measure this in practice? What we do, in fact, is that we measure the ellipticities of galaxies. And the observed ellipticity of a galaxy depends on the, not just independently either the shear or the convergence. It depends on this combination of the shear and the convergence called the reduced shear. So the reduced shear is just the shear over 1 minus the convergence. But as I said earlier, for individual sources, both of these quantities are really small. So typically what we do to make life easier is that we approximate this convergence as being really small. We Taylor expand that, and then we just say that the reduced shear is equal to the shear. And then the ellipticity is just equal to the kind of unlensed ellipticity plus the shear. And the statistics of what we're actually seeing, which is the reduced shear, are just equivalent to those of the shear. And this is known as the reduced shear approximation. And then to really get a kind of redshift dependent picture, we can basically bin the galaxies that we observe in redshift bins and carry out measure power spectra for each of these bins. But in addition to the reduced shear approximation, there is a whole plethora of assumptions that we make in these analyses to make our lives easier, and systematic effects that we neglect. So we make, this is kind of a list of a few. There's many more, but there's the flat sky approximation, where we assume that the angular extent of the field that we're observing is small, and that we can just use planar transforms in some places rather than spherical ones. Then there's the Limber approximation, which I think you had another seminar about recently, or will have, where essentially you only include contributions to your lensing signal from correlations in the plane of the sky. It's a little bit more complicated than that, because you don't exactly neglect the ones not in the plane of the sky. You kind of use a projection to basically project them into the plane of the sky. Then there's intrinsic alignments. So I mentioned earlier that the observed ellipticity depends on the unlensed source ellipticity and the cosmic shear term. But in fact, that is under the assumption that in the absence of cosmic shear, the ellipticities of galaxies in the universe would just be randomly distributed. But in fact, that's not strictly true, because some galaxies form under similar tidal environments, and they have some kind of intrinsic alignment, which is not attributable to cosmology. So when we're measuring the ellipticities for the purpose of extracting cosmology, we need to model this non-cosmological intrinsic alignment signal and remove it. And we have some pretty decent models for that. Then there's the reduced shear approximation, which I talked about there, which is basically that you approximate the statistics of what we're seeing, which is reduced shear, to be equal to the statistics of the shear itself. And then there's something called magnification bias, which is that which is really kind of an effect of the fact that your instrument, whatever it is, will have some flux limit. And individual galaxies that are kind of sitting around the flux limit of your instrument, either just within or just outside, because when their size is changed by the magnification, their flux changes. They can either be included or excluded from your sample, and that can affect your number density that you measure from to no longer be representative of the true number density. So a lot of these have already been kind of evaluated, so the flat sky approximation, limb approximation, and found to either have, readily available corrections or are not to be particularly significant for upcoming surveys. But the two that haven't really until this point, and that I'm kind of looking at, are the reduced shear approximation and magnification bias. Now, those are quite different, effects. One is very much just a kind of mathematical theoretical thing that we do to make our lives easier, and the other is a, sort of instrumental, sort of cosmological effect that we just neglect again to make our lives easier. So why do we treat them together? Well, we actually get quite fortunate mathematically, because as it turns out, and I'll show you, their corrections take mathematically very similar forms. So we can basically compute both of those for the computational cost of one. So just to, just if anyone who's kind of interested in the maths, or just to remind those who've already, of course, seen this a lot, this is how we define the weak lensing angular power spectra. So it's basically just an integral over the matter density power spectra weighted by the lensing kernel. So it's basically just accounting for all the curvature and the particular structure of all the matter in between. So the first thing, of course, is to find out how wrong are we when we consider reduced shear and magnification bias, So how do we go about doing that? So it's still quite complicated to, take just the 2-point statistic off G, because you have, of course, this is really non-trivial to compute. So we can still make our lives easier a bit by just doing the oldest trick in the physics textbook, which is taking a Taylor expansion. But now, instead of just stopping after this first, shear term, we keep going to the next order. And what you get is, you get a term that is basically a gamma kappa term. So it's proportional to, well, it is the shear times the convergence. And then when you take that through all the way through to the maths, to the shear power spectrum, you end up with your original shear power spectrum plus a correction term of this form, this kind of 3-point term now. And that correction term, in the same way that the angular power spectra was dependent on the matter power spectra, the correction term is now dependent on this this bispectra, which confusingly I know, but it's actually the 3-point term. And the reason for this integral over L is because now when you go into Fourier space or spherical harmonic space, this is the conjugate of gamma kappa multiplied together rather than gamma and kappa individually. So you have to do a convolution, basically. So that's the kind of form of the correction for reduced shear. What about magnification bias? So I mentioned briefly that what magnification bias is that essentially the observed number density of galaxies that you observe is affected by the lensing, the magnification part of the lensing, because your survey has a flux limit. So this is actually two competing effects at any given point. Individual galaxies are magnified. So individual galaxies that may sit just on just outside your, the flux limit of your survey are magnified such that their flux is increased. So they're suddenly within the flux limit of your survey. So this increases your observed density. On the other hand, the density of galaxies in the patch of sky around these magnified galaxies is diluted because the patch is also slightly magnified. And both of these effects can also go the other way. And in fact, altogether, the effect depends on the convergence and the slope of the luminosity function. So that's all that is there, the S, and the 5S minus 2 comes from basically converting between like fluxes and luminosities. Yeah, so, and that's what your observed galaxy number distribution looks like, and that's the kind of unlensed true galaxy distribution that you would get. So when you then take this through in your theory to the shear, what ends up happening is that you end up seeing that the shear that you're actually, that you're computing theoretically shouldn't, using this number density, should have this additional correction term, which again is, is this kind of gamma kappa term, just with now this factor of 5s minus 2. So you'll recognize that this is the same form as the kind of second order reduced shear correction, just with this additional factor on the end. So what that means is that basically we can compute this term, and then this additional luminosity function term is, doesn't take very much computational power at all. So essentially we can correct for these two terms for the cost of one. So as I mentioned before, both of these correction terms then are dependent on the convergence bispectrum, which is basically the 3-point statistic of convergence. Analogous to how the matter power spectrum is a projection, analogous to how the weak lensing power spectrum is a projection of the matter power spectrum, the convergence bispectrum is a projection of the matter bispectrum. But now it depends on, kind of 3 factors of the lensing kernel, and also the curvature of the universe in a different way. But we run into a problem here because the matter bispectrum is relatively poorly understood, and the only way we have to work out its nonlinear behavior is to use fitting formulae to n-body simulations, and even those are less developed than the ones we have for the matter power spectrum. So that's the kind of framework for addressing these corrections, but in practice, how do we actually go about quantifying that? So as I said right at the beginning, I'm kind of focused primarily on a Euclid context. So what I did was, okay, let's take the Euclid survey specifications and compute the corrections for that. And that's what we did using a fairly standard kind of Planck 2018 cosmology. So these are just, these are kind of predicted specifications for the Euclid weak lensing survey. So an optimistic L max of 5,000. So L is the Fourier conjugate of theta angle on the sky, basically, and the limiting magnitude of the survey is 24.5. And then when you do that, this is basically what we saw. So what you see here is each of the 3 plots is the relative magnitude of these corrections. So the leftmost is just the reduced shear correction to the angular power spectra relative to the true shear power spectra, as well as contributions from intrinsic alignments. The middle panel is the same, but with just the magnification bias correction. And then the rightmost panel is the 2 corrections combined. And let me unpack what's happening here is basically that the reduced shear correction in terms of magnitude is generally lower than the magnification bias correction, which is unsurprising because of course the magnification bias correction has that additional factor on the front, but it is always positive. On the other hand, the magnification bias correction at lower redshifts is actually negative. So that means that dilution effect is kind of winning out over the increasing effect in the number density. Whilst at higher redshifts, it's the opposite. And actually, the higher redshift correction in magnitude is generally much higher than the lower redshifts ones. But then when you combine the 2 corrections, you get something interesting, which is that at the lowest redshifts, the two corrections actually cancel each other out. But this is almost not important, dare I say, because most of the power of these correction terms is at the highest redshifts anyways. And you can see that like at the highest redshifts, the two corrections just kind of add together to make an even stronger correction term. So we know that, we know, okay, there is a correction term that is non-trivial, but this number looks really small, right? This is like 0.05% of the shear power spectrum plus the intrinsic alignment terms. So what does that actually mean in terms of what we care about, which is cosmological parameter inference? So to do this, we adopt a common thing in cosmological analysis. Instead of doing a full Monte Carlo, which can take lots of time, and in particular is a challenge because of that bispectrum expression I talked about, to compute that is a huge computational challenge. Instead, we use Fisher matrices. So a Fisher matrix is just the Hessian of the log likelihood. And basically, if you invert the Fisher matrix and take the diagonal, the square root of the values of the diagonal will give you basically one's predicted 1 sigma constraints on your parameters. So this is what a Fisher matrix expression for weak lensing looks like, assuming a Gaussian likelihood. And then you can similarly also consider, if you have some systematic in the data that is not taken into account, how much will that bias the parameters? It's relatively straightforward to kind of modify the Fisher matrix expression for a kind of delta CL term, and this is what you get. In practice, actually, for this part of the analysis, we didn't just use the Gaussian likelihood. We also included contributions from what's known as the supersampled covariance. But this is just kind of for simplicity, but I can discuss that later as well if people have questions. And then when we do that, this is what we find. So for both of the correction terms individually, we find that there are significantly biased cosmological parameters. So what we consider significantly biased is, it's a fairly standard measure, is if the bias exceeds 25% of the predicted 1 sigma error. And the reason for that is at that point, the projected parameter contours would overlap by less than 90% for the biased and unbiased predictions. So we see that, for example, for the reduced shear approximation, all 3 dark energy parameters are significantly biased. And given that better constraining dark energy is one of the primary goals of Euclid, and indeed experiments like Rubin and Roman, this clearly shows that we really need to take into account reduced shear. But then also when we go to magnification bias, it's much worse because, of course, the magnification bias correction was larger. And what we see is that now not only are the dark energy parameters biased, need to be careful with the trackpad, but also now omega m, the spectral index, and the sigma 8, which is essentially the amplitude of the matter power spectrum, are also significantly biased. So basically, we do need to take both of these corrections into account going forward. And this is just what the projected 2-parameter contours look like with the bias corrected and without it corrected. And you see in some cases, the difference is really quite large. I mean, this is probably the most worrying case, where the contours don't even overlap at all. But there is a problem here because, as I mentioned, to compute this correction term in this form is very computationally intensive. So to give you an example, for just one cosmology to compute these corrections, it took 24 hours on a 100-core machine, fully parallelized. So even though we have this way of correcting it, that there's still an issue that's not like entirely solved there, at least for this part. So those are 2 kind of systematic effects or approximations that we neglect. But the fact is that those 2 things don't exist in a vacuum. Even when dealing with those systematics and correcting for them, we make other approximations. So I kind of said, I had it on the slide. I don't think I mentioned it, but for example, when computing the convergence bispectra, we make the Limber approximation. So that begs the question: does the interdependency of some of the corrections for these approximations or the approximations themselves introduce additional biases, and are they significant? So one of the first things we looked at is how do reduced shear and magnification bias come into play with the intrinsic alignment terms? And the thing is that they affect the intrinsic alignment terms too. And the reason for that is, under the approximation of reduced shear and, well, under the reduced shear approximation and neglecting magnification bias, this is how intrinsic alignments are treated, right? So I said you have the ellipticity that you observe is dependent on the kind of source, true, unlensed ellipticity of the galaxy. If it was like in, completely by itself, no tidal environment, plus the cosmic shear term, which is from the weak lensing, and then this kind of intrinsic shear term, which I said is from because galaxies, of course, form in similar environments. And then, when you take that through to the 2-point statistic level, what you end up with, of course, is your standard 2-point shear term. Then you get a shear intrinsic term, and then you get an intrinsic term. But of course, if we kind of put in the next order expansion of G, or alternatively, just that kind of gamma plus gamma kappa term from the magnification bias, you now end up with these 6 kinds of terms, right? So you end up with the first 3 terms that you had with just the standard intrinsic alignment model. Then you end up with your, reduced shear term, your 3-point term that was dependent on the bispectrum or your magnification bias term. Then you end up with a term that is, proportional to the shear convergence and now one of the intrinsic alignment terms. And then you have a 4th order term, which has been shown to be negligible. So it's really this term that we're interested in now. So the question is, how does this affect the biases? Is it significantly biasing by itself, or does it make any, of the other biases significant? Fortunately, when we compute these, we find that actually the intrinsic alignment, reduced shear, and magnification bias terms are safely negligible. So all the biases that they cause are well below, 25% of sigma. And you can see that in the projected constraints here, where there really isn't any sort of significant overlap. Sorry, or they are basically completely overlapping. There isn't not any significant overlap. So, okay, that's intrinsic alignments, but what about the Limber approximation? So just to recap, in case you're not familiar with what the Limber approximation is, the Limber approximation is essentially the fact that of course, when you look at correlations, there will be some correlations that are not truly in the plane of the sky. There'll be correlations that are kind of like that or something, So what you do when you make the Limber approximation is that you basically kind of projecting them into the plane of the sky. And mathematically, what that boils down to is that in kind of the integrals that you do when computing the angular power spectra, you're replacing Bessel functions, spherical Bessel functions, which are notoriously difficult to integrate, with delta functions, which are nice and pleasant. So you do that even in this integral for the bispectrum, right? So now we want to see what about the non-Limber case? What happens in that? So how do we calculate that? Well, firstly, we can separate. What helps us is the separability of the matter bispectrum. So you can write the matter bispectrum, because it's dependent on some fitting formulae, as a kind of combination of cyclical permutations of the matter power spectra. And then you can basically write it in this full way with the spherical Bessel functions included. I won't go into too much detail because this is all maths. And as I said, essentially what you do when you're making the Limber approximation is that you're approximating this integral over these spherical Bessel functions as just being a delta function. And that greatly simplifies the corrections that we have to make. So the first thing that we did is we just computed the post-Limber bispectrum. So what we found is that essentially, if any sides of the bispectrum triangle, so if any of the correlation L modes that you're using are less than 100, then you will need to take into account this post-Limber part. So basically what you're seeing here on the left is an equilateral configuration for the bispectrum. So that means all the sides are the same. So all 3 L modes are equal. That's what's going on here. And again, you see that, above around like 60, then the Limber approximation works great. Then these two are 2 different isosceles configurations. So where 2 of the sides are equivalent and a third side is kept fixed to some value. And you see that when third side is kind of below 100, then it doesn't matter what the other 2 sides are doing. The Limber approximation is always over predicting the true bispectrum. And then here, when you see that one side is 100, then as soon as like the other sides are, close to 100 as well, then again, it's equivalent. So yeah, it's interesting because if the bispectrum is something you want to measure, then this is probably something you'll have to take into account if you're going to go to scales below L of 100, which you may not, because that's those are quite large scales. But what about taking that through to the biases that I was talking about, the reduced shear and magnification bias corrections? Because we over L over the spectrum, what we actually get mode mixing. So what that means for our corrections, that discrepancy matters at all L modes. We slightly overpredict, if we make the limb approximation, those correction terms at all L modes. But again, that mode mixing actually is good because the L mode, the contribution from L modes between like 0 and 100 is very small because there's all these other L modes, right, that you integrate over. So what that essentially happens is that although there is a slight reduction, if you take that through to, if you measure the difference between that, it's always well below sample variance. And we even, in the paper, we even actually did like a worst case scenario calculation where we took the kind of worst discrepancy, so of like 10 to the minus 2, and we applied it to all L modes for all redshift bins, and we did a Fisher analysis just to see kind of as a worst case scenario, is it significant? And we found that it's not. So in truth, in fact, it's not at all significant. The worst bias we found was about 10%, but given that in practicality, most of the discrepancies are actually well below that, it wouldn't even be that. Then, I mentioned that that we don't have like an exact analytical expression for the matter bispectrum. What all we need to do is use n-body simulations and then kind of get fitting formulae from that and use those to model the nonlinear behavior of the matter bispectrum. So what we did to kind of check how sensitive the corrections were to the particular model of the bispectrum you use as well, is that we checked kind of two of the commonly used approaches. So up until relatively recently, the approach has been to start from second order perturbation theory and then kind of tack on some fitting functions which fit the expression that you get from second order perturbation theory to n-body simulations. And there's been kind of two major fitting formulae for that, one by Scochamaro and Couchman in 2001, and then another more recently by Gil Moran et al. In 2012. So this was the one model that we tested. And we chose to use the Scochamaro and Couchman one just because it's the most different from the more recent model, which I'll talk about in a sec. And from here on out, that model is denoted by SC. And then really recently, like this year, a new approach has come out, which, I mean, it's still a similar approach because at the end of the day, you still have to fit to n-body simulations. But it's this kind of halo fit approach. And halo fit has been used for a while to model the nonlinear parts of the matter power spectrum. And the way it does that is it has these like 1H and 3H terms. So all they did in this work is, well, I say all, but what they did in this work is that they applied this formalism to the bispectrum, and then they derived a fitting formula for n-body simulations for these 1H and 3H terms. And that was the other model we tested. So there we used their publicly available code. And that's denoted by BH in this next part. So basically what we found is that taking the ratio of the correction using the bi-halofit model or the Scochamaro and Couchman model was actually generally not that different from one. And in fact, the biggest differences which occur at lower L's occur at points when the correction terms itself are quite low. You see at higher L's which is where those correction terms are most significant, the differences are actually quite close to 1. And we kind of computed the biases from both of these models, and we found basically that the difference in the biases was tiny. So it's reassuring because it means that with the exception of like our understanding of the bispectrum being like really completely catastrophically wrong, whatever evolutions happen of this bispectrum model, these correction terms are relatively robust to that. So we can use whatever correction terms we want, even though we still have the problem of any one of those formulae still taking a long time from the perspective of wanting to do a Monte Carlo. So now finally, I'll talk about a recent paper where we kind of proposed one potential solution to the problem, and that's using something called K-cut cosmic shear. So, fortunately, we don't have to worry about the post-Limber case. So we can happily, use the Limber approximated corrections, and we are robust to the choice of, the choice of bispectrum, and we don't need to worry about those additional intrinsic alignment bias terms either. But as I said, doing it that way, where we calculate that correction explicitly, still takes 24 hours to compute for one cosmology, even multiprocessed across 100 CPU cores, right? Which is just intractable for Monte Carlo analysis. You just can't use that if you want to do like a Markov chain with however many thousand steps. So one approach, of course, very conservative approach, is that we could just take a scale cut at something like L of 1500. And the reason I singled that out is because in the recent forecasting paper for Euclid, that is proposed as a kind of conservative scale cut to remove sensitivities to the nonlinear part of the matter power spectrum. And it would also remove sensitivity to all these additional corrections as well. But that actually significantly weakens the constraints that we get, and it actually weakens them to the point where Euclid wouldn't be able to meet its goal for weak lensing precision. Now, the alternative is that we could take a K-cut, and a K-cut would translate into basically a redshift dependent L cut. So K-cut would basically be equivalent to like taking a cut at some physical scale. In like a hypothetical shell universe, we could simply use the Limber approximation and just take a K-cut at some L above some K-cut defined value, like times co-moving distance. But in practice, the shear lensing kernels are broad. So in the top panel, you see what the actual shear lensing kernels for Euclid are projected to look like. And what that means is that lenses across a range of distances and scales contribute power to the same L mode. So what we can actually do to kind of mitigate the effect of that is that we can perform something called a Bernardo-Nishimichi-Teruya transform on the observed power spectra. And this is effectively what this does is that it reweights the spectra so that each bin only contains information about lenses in a narrow redshift range, which is what's happened here. And this technique was pioneered by my colleague Peter Taylor, who is now at JPL. So you see that actually, there is still overlap between the kernels here, but it actually turns out, you can see it in Peter's earlier papers, that that overlap is small enough that it doesn't significantly affect the K-cut procedure. So what we can do now is that we can, for each redshift bin, for each reweighted redshift bin, take that K-cut, that kind of K-cut, so L above some defined K-cut value, and the mean co-moving distance of said bins. So this is what we see when we do that. So basically what you see here is that for a variety of parameters, and it's actually a different set of parameters to previously, because for this paper we had to use a different cosmology. Here we just assumed flatness. And basically what you're seeing is how the bias as a proportion of the 1 sigma constraint on each parameter changes with a varying K-cut. And basically, you see that you don't have to take a very aggressive K-cut at all to make the biases no longer significant. And so that's like 5.3 H megaparsecs, or inverse megaparsecs. And actually, when taking that K-cut to no longer make reduced shear significant, it compromises the actual parameter constraints very little compared to taking a more aggressive L cut. I think with this scale cut, all but 2 of the parameter constraints increase by less than 10%, whereas if you take like the conservative L cut, then all but 2 of the parameter constraints increase by more than 100%. So yeah, it's a significant improvement over that. So this is definitely one. You do lose some information, but you lose a lot less information than if you were just taking an L cut somewhere. This is just, the explicitly in numbers, the uncertainty when you take the uncertainty, in the case where you've included full L up to 5,000 and you've like fully theoretically modeled that correction, or the uncertainty where if you've taken that K cut from before, or the uncertainty in these parameters when you take like a scale cut at 1500. But I should stress that you're not taking the K cut to deal with reduced shear or magnification bias, right? You're taking the K cut because you want to avoid modeling some of the nonlinearities in the power spectrum, because those are difficult to model. It's just that when you do that, you actually basically get this correction out for free. And because in practice, to deal with the the nonlinearities, you'll take a lower K cut than what you need to take for these. It's just something that is also solved one potential way by this. So yeah, I mean, that's basically everything. So just to conclude, the motivation for this work is that next generation cosmic shear surveys like Euclid, Vera Rubin and Nancy Roman will offer more than an order of magnitude leap in the precision of their data. So we need to keep up our accuracy of our theory with the precision of those experiments. And the two corrections that I've looked at together are reduced shear approximation and magnification bias. But unfortunately, the kind of explicit calculation of those corrections is computationally intractable for an MCMC in any kind of realistic situation. But one way that we can solve that issue is to apply the K-cut cosmic shear technique. So yeah, that's everything. Thank you for listening, and